All right, welcome to this explainer. Today, we're popping the hood and demystifying the black box of how data scientists actually choose and optimize the absolute perfect machine learning models. I mean, think about it. A poorly tuned model, that can cost a company millions in miscalculated predictions. But a perfectly optimized algorithm, that right there is your ultimate competitive edge. So if you've ever wondered how an algorithm goes from just a basic concept to a highly tuned predictive engine, well, you're in exactly the right place. You can kind of think of this whole process like casting a massive blockbuster superhero movie. You have to audition different candidates, put them through some pretty rigorous rehearsals, and then meticulously direct their final performance. You wouldn't just hire the very first person who walks through the door, right? Well, in data science, we definitely don't just use the first algorithm we try either. To get to that perfect performance, we've got a clear roadmap for today. Choosing the right model, probabilistic versus resampling methods, mastering k-fold cross-validation, what are hyperparameters, and finally, grid and randomized search. All right, let's dive into section 1, choosing the right model. So this is basically our initial casting call. We're evaluating different candidate algorithms to see which one actually fits our data best. And the crucial thing to remember here is that model selection isn't just about picking the flashiest or, the most complex algorithm available. It's a highly calculated decision. Whenever we select a model, we're constantly doing this balancing act. We're obviously looking at performance metrics, accuracy, precision, absolutely. But we also have to consider the complexity of the model. Actually, a simpler model is often way better because it's easier to interpret and maintain. Like, you might be totally tempted to use a massive, super complex deep neural network, but if a simple linear regression gives you 95% of the accuracy in a fraction of the training time, that might actually be the much better hire. We also got to weigh the training time, how well the model scales when our data blows up, and the actual computational resources we have sitting in front of us. Moving right along to section 2, probabilistic versus resampling methods. Okay, so once we actually have our candidates, how do we fairly evaluate them? If you just rely on the training data to evaluate a model's true capability, you're falling into a trap. Why? Because the training error is optimistically biased. It's literally like asking a student to take a test using the exact same questions they just studied. Obviously, they're going to ace it. So, we have two main schools of thought to fix this. On one side, we have probabilistic methods. These analytically score a candidate model and mathematically penalize it for being too complex. Basically, models with fewer parameters are rewarded because they usually generalize better out in the wild. Think of things like the Akaike Information Criterion, AIC, or the Bayesian Information Criterion, BIC. On the flip side, we have resampling methods. Instead of mathematical penalties, this method forces the model to actually prove itself on unseen out-of-sample data. This is where you see techniques like random train/test splits, bootstrapping, and cross-validation. Which brings us nicely to section 3, mastering k-fold cross-validation. Let's zoom in on that last resampling method because it is incredibly popular in the field. This is how we put our model through those rigorous rehearsals we talked about. To make sure our model doesn't end up being a one-hit wonder that only understands its specific training data, we use k-fold cross-validation. And it follows a really logical, chronological process. First up, we partition our entire dataset into multiple equal-sized subsets, which we call folds. Second, we train our model on a combination of some of these subsets. And third, we validate or test the model on the remaining unseen subsets. We just repeat this until every single slice of data gets a turn being the test set. If you look closely here, you can see how this plays out for a 5-fold cross-validation. Notice how the validation slice shifts diagonally across the matrix. Across 5 different splits, a different fold gets a turn acting as the test data, while the rest of the data is used for training. By rotating through the data exactly like this, we get 5 different performance scores. We average them all out, and boom, that gives us a highly reliable, completely unbiased estimate of how our model is actually going to perform in the real world. So, all right, at this point, we've successfully chosen our model, and we've validated its baseline performance. But that really begs the question, doesn't it? How do we know we're using its absolute best settings? Is the model truly running at its absolute peak potential? Let's find out in section 4, what are hyperparameters? If model selection was the casting process, well, this is where you step right into the director's chair. We really need to differentiate between two concepts here. In machine learning, regular parameters are the weights and biases that the algorithm learns entirely on its own from the data. It does that automatically. But hyperparameters, those are the physical dials turned by the human data scientist before the training even starts. They dictate the actual behavior of the training algorithm itself. And depending on the actor we selected, the dials we have available to turn completely change. For example, say we chose a neural network. Our hyperparameters are going to include the learning rate, which dictates the step size the optimizer takes, the number of epochs, the number of layers and nodes, and the activation function. But if we chose a support vector machine, or SVM, we are tuning totally different things. We'd be adjusting C for regularization, picking a kernel type like linear or polynomial, and tweaking gamma to control the influence of our support vectors. The ultimate goal is to find the perfect combination of these settings. I mean, turning these specific dials just slightly to the left or right can literally be the difference between a model that merely guesses and one that makes highly accurate, incredibly profitable predictions.
So how do we turn those dials? Section 5, Grid and Randomized Search.
Finding that perfect combination is definitely no easy task. Our first systematic strategy for finding this perfect setup is grid search, which you might know in Python scikit-learn as grid search CV. This is the most exhaustive, leave no stone unturned method available to a data scientist today. Just look at how every single box in this matrix is highlighted. If we have parameter 1 on the top and parameter 2 on the side, grid search systematically evaluates absolutely all predefined combinations of these values. It's going to train and validate a model for combination A1, then A2, then A3, and so on, until literally every single box has been tested. It is mathematically guaranteed to find the best configuration from the options you give it. But, as you can probably guess, evaluating every single box like this takes a massive amount of time and a ton of computational power. Because of that huge computational cost, if your model is highly complex and your dataset is just massive, you might want to opt for our second strategy, randomized search, or randomized search CV. Notice the stark difference here. Instead of checking everything inside the entire grid, randomized search selectively samples random combinations. It just checks a fixed number of random settings. Now, this saves absolutely massive amounts of computational resources. And mathematically, it still has a very high probability of finding excellent near-optimal settings, especially when your search space is huge. So, summing up these two titans of tuning, it always comes down to balancing thoroughness against scalability. Grid search gives you that exhaustive peace of mind, sure, but it kind of leaves you staring at the hourglass. Randomized search, on the other hand, brings lightning speed and way better scalability for large datasets, at just the slight risk of missing the absolute mathematical peak. Ultimately, your choice depends entirely on the computational resources you actually have on hand and just how complex your chosen model is. And wow, that brings us to the end of our journey through model selection and tuning. We've cast our algorithm, we rehearsed it with cross-validation, and we directed its final performance by tuning those hyperparameters. So I'll leave you with this final thought to consider for your own data science projects. Perfection is costly, both in terms of computing power and time. When you finally sit down in the director's chair, how will you choose to balance your resources against the quest for your model's ultimate performance? Thanks so much for joining me for this explainer, and hey, happy tuning!